Welcome back to the training series for the Rehabilitation Cost Estimation tool for mining and exploration in New South Wales. This is Module 12. The Active Mining Area Input Sheet calculates costs for rehabilitation of mining areas, primarily pits. Tables are available for safety bund, fencing and signs, drill and blasting of benches and high wall and dozing to make safe, shaping of low wall and load and haul to make safe, backfilling of open pits and ramps, removal of contamination from ramps, construction of drains and water management, source and apply growth media and ameliorants, revegetation, maintenance and repair of rehabilitated areas, and waste management and contaminated soil treatment. As for all the sheets, we enter the name of the item, any notes, and a GIS reference if available. The GIS reference can be the object ID of the polygon associated with the active mining area uploaded as part of the annual rehabilitation report submission into the regulator's Mine Rehabilitation portal. The void surface area is the key input, and this is used in the land rehabilitation tables and as a general reference throughout the tables. The sheet has the same flexibility as the others in that we can use several columns or just one. We will enter 3 examples with footprints of 50 hectares, 20 hectares, and 10 hectares. Please note that the quantities used for these examples do not necessarily reflect real-life projects, and it is up to you to ensure your quantities are accurate. The first treatment table is constructing safety bunding and installing fencing. For safety bunding, we enter the length of bund to be constructed. We will enter 20 kilometers in 2 columns to show the differences between safety bund amounts. The defaults for the bund dimensions are in the Assumptions General sheet here. These cannot be changed by the user. The tool calculates the specific volume of material and the surface area, that is, the footprint of the bund. The specific volume is the volume per meter of bund. The construction method selection allows us to select whether material for the bund will be hauled from an area not at the construction site or excavated from the construction site. We can now see the difference in cost between the 2 methods. The next sections are for fencing and signage, and inputs for these are simple. Our third example does not have a safety bund, so we will leave those entries blank. This example needs 100 kilometers of fencing to secure the open pit and 20 kilometers of higher fencing to secure the high wall. We will put signs on all of this fencing, so enter 120 kilometers to the Install Signs row. The safety bund and fencing table is now complete. The next treatment is high wall, benches, and drill and blast, which includes dozing to reshape and make the area safe. We enter the volume of soil in the high wall and benches to be blasted and the amounts to be pushed by the dozer. We will enter 500,000 cubic meters for the high wall volume for the first pit, 200,000 for the second, and 100,000 for the third. We will then add 100,000, 50,000, and 20,000 respectively for the benches volume. The drilling and blast costs are now shown. We need a larger dozer for the bulk push, so we select a D11 in each case and the 100 meter push length category. The next section is for reprofiling, and we enter 20, 10, and 5 hectares. The slope angle and dozer size determine the reprofile unit rate, and this is multiplied by the area to be reshaped to get the cost for that activity. As for all slope angles for dozer push, the higher the number, the steeper the slope, and consequently the less effort the dozer has to exert, and the lower the unit rate cost. Further, unit rates for dozers are lower for larger machines when the productivity outweighs the increase in hourly cost. The cost for the high wall and benches are now complete. The next treatment is for low wall shaping. This activity comprises reshaping, pushing, and constructing a bund. We first need to enter the volumes to reshape, and we will enter 100,000, 80,000, and 20,000 cubic meters. We will use a D8 dozer, and the average push length in each case is about 50 meters. We then enter the areas to be reshaped, which will be 10, 5, and 2 hectares. Then select the reprofiled slope angle, which is downslope, and the dozer size. The last table in this section is for load and haul of rock to create a bund. We only need one for the first pit, so we will enter the volume, 20,000 cubic meters in this case, select a medium fleet hauling rock from 1,200 meters away, and leave the others blank or enter 0. For the 2 pits not requiring rock, we will enter a note to inform the regulator. The next treatment is backfill of the open pit and ramps with waste rock. We will show 3 examples to demonstrate on- and off-site methods. For our first pit, we are required to backfill 1 million cubic meters of pit void and 100,000 cubic meters of ramps. All our rock is available on-site, so we select on-site rock and set the on-site source row to 100. The tool calculates the volume of on-site rock by multiplying the volume quantity by the percentage input. We can see the volume of off-site rock is calculated as 0 for this example. For on-site rock, we select the load and haul distance, which will be a medium fleet hauling from 3,000 meters. The next section is for off-site haulage, and this is calculated as 0. The last section is for dozing and leveling, and we will select a D11 dozer with push length 75 meters. The volumes entered to backfill the open pit and ramps are multiplied by the rate to get the cost. For our next backfill example, we must obtain all our material from 50 kilometers away. We select offsite VENM, which is virgin excavated natural material, and set the proportion of onsite source to 0. We can see that the tool sets the onsite volume to 0 and the offsite volume to the full volume. The load and haul for onsite section is set to 0, and we move on to the offsite section where we select the one-way haul distance. However, in our example, we will not worry about a distance as we have a quote for VENM delivered to site of $75 per cubic meter. We enter the 75 to the alternate rate for offsite sourcing and set the alternate rate for cart offsite source to 0 as the transport cost is included in the quote. As always, we leave a note for the regulator. If we have a quoted cost for transport separate to the purchase cost, we must calculate the dollars per distance per volume rate and enter that to the alternate rate for cart offsite source. We do this by dividing the transport cost by the one-way distance and then the volume to be carted. For example, if the transport cost is 100,000, one-way distance is 10 kilometers, and the volume is 20,000 cubic meters, our calculation is 100,000 divided by 10 to get 10,000, then divided by 20,000 to get $0.5 per kilometer per cubic meter. For our last example, we will show how to account for a combination of on- and off-site sources. We will assume 30% is coming from off-site, so we change the proportion of on-site source to 70%. The selection of on-site rock or off-site VENM does not matter in this case. You can see the tool calculates the on- and off-site volumes. We will leave all the other selections the same for this example. The last treatment is for rehabilitation of ramps. All of these quantities must be entered to calculate the cost. We will show an example where the depth of contaminated ramp material to be removed is 0.5 meters from a total depth of 1 meter. We enter 1 and then 0.5, and then the width of the ramps, we will assume 10 meters, then the average length of the ramps, we will assume 10,000 meters, and then the number of ramps, where we will enter 1 here to show the per unit cost, and then 2 here to show the multiplying calculation. We then select the fleet sizes and distance for each activity, which includes pushing up the contaminated material and replacing with fill. We will select D8 dozers pushing over 20 meters and a small fleet hauling material from 2,000 meters away. This completes the pit treatments, and the remaining tables are for drainage, land rehabilitation, maintenance, and managing any contaminated soil and waste. Let's recap those now. For drainage and water management, we must enter the area over which drains will be constructed and select the type of drain. In our examples, we will assume the areas are the footprints we entered at the beginning of the sheet, so we enter 50 hectares, 20 hectares, and 10 hectares in both the drainage and water management area rows. For the first example, we will construct 4-meter wide drains, 8 meters for the second, and spine drains only for the last. If we require 2 or more types of drainage, we can enter to adjacent columns. For the land rehabilitation tables, the tool suggests the area for each element, such as safety bunds, benches and high wall, and low wall, that were entered in the corresponding tables. We can change any of these areas if we need to. For the first example, we will accept the defaults suggested by the tool and select a one-way haul distance of 2,000 to 2,500 meters. For the next example, we will accept the suggestions for the area, but have information to show that a growth media thickness of 100 millimeters is acceptable and/or the default is not achievable due to the nature of the site. We override the default by entering 0.1 meters and leave a note for the regulator. We then select the one-way haul distance of 2,000 to 2,500 meters. For our last example, only half of the area must be rehabilitated as the pit is in an arid type area, so we override the areas. We select the one-way haul distance of 2,000 to 2,500 meters. For ameliorants, our studies show we need to amend the growth media in the first pit with gypsum to create a soil structure conducive for vegetation growth. The second pit we amend with lime to correct a pH balance. The third pit does not require any treatment. For the first pit, the safety bund area does not require treatment, so we set this area to 0 and accept the other defaults as suggested. For the third pit, we must override all the suggested areas with 0 so that no ameliorant cost gets added. For revegetation, our first pit is in pasture, the second in native vegetation, and for the third pit, half of the area will be treated with hydromulch. We will accept all the suggested areas for the first two, override the areas for the third, and ensure our selections down each column are consistent. That is, all pasture for the first, all native for the second, and hydromulch BFM with native seed for the last. The next section is maintenance of rehabilitated areas and repairs. Remember, while it assists understanding if columns are dedicated to one element, for example a specific pit, it doesn't have to be done this way, and in some cases we will need to use more columns to cater for all activities required. To demonstrate how several land treatments may be applied, we will assume all these are required and enter 10 hectares along the columns. That is, 10 hectares for pest management, land management of undisturbed areas, existing rehabilitation repair minor, moderate, major, total failure of landform, and maintenance of areas that are shaped and seeded and revegetation has been successful. None of our pits have any significant waste or contaminated soil issues, however there is 1,000 tonnes of concrete rubble in Pit 1 that was left over from a past project. We will cart it 50 kilometres to a facility and pay the regional levy. As always, if there are additional items not covered in this sheet, they can be added here. As for all the sheets, the subtotals for each table are shown in the black lines at the end of each section, and then the total for each column is shown at the top of the sheet. For this sheet, the tool also shows a per hectare rate. The total for the sheet is shown on the left-hand side, and then above that is the total for the entire RCE, so we can see in real time how quantities entered to the local sheet affect the total RCE. Let's jump over to the RCE summary to see how the total is building up. We now have rolled up costs for infrastructure area, infrastructure mine entries, beneficiation facilities, tailings storage facilities, water management areas, overburden emplacement areas, and now active mining areas.